Okay, so again, when we're drawing Lewis structures, we want to follow this very systematic approach, right? We always start by counting the total number of valence electrons. We then write what we call a skeleton structure by connecting all of the atoms with single covalent bonds. Each of those single bonds corresponds to 2 valence electrons, and then we're going to try to satisfy the octet rule. Okay, and again, this octet rule, it says that whenever possible, the electrons in a covalent compound are distributed in such a way that each main group element is surrounded by 8 valence electrons, okay, or an octet. Now, there are some exceptions to this rule that we're going to see later, but for now, we're going to try to satisfy the octet rule, and it works really well in many simple cases. Okay, so let's do a few more examples. So start off with something like, I guess I need a pen. So I'm going to start off with, not in green, I'm going to start off with HCl. So the hydrochloric acid molecule. So in the gas phase, this is a molecule. So the first step, count the valence electrons. Each hydrogen has 1. Each chlorine, being a halogen, all of our halogens have 7 in group 7. Okay, so we have 7 valence electrons. Okay, and so we start with a skeleton structure, HCl. That accounts for 2 of our valence. I'm sorry, we don't have 8. Each chlorine has 7. We have a total of 8 valence electrons here. Okay, 1 from the hydrogen and 7 from the chlorine. Okay, so we have 8 valence electrons. There are 2 in our single bond connecting them. Now, we can't have more than a single bond here because that's all that hydrogen will accommodate. So we're going to try to satisfy the octet rule for our chlorine by using lone pairs. So we go 1, 2, 3, 4, 5, 6, and we are done. We look at this and we've satisfied our octet rule, 2, 4, 6, 8 electrons. We have a single bond to hydrogen, and so this is a good representation of the HCl molecule. Again, these lone pairs have some importance, and we want to always include them. And one of the things we're going to notice for halogens is whenever they are a peripheral atom, that is, they're not a central atom, they're generally going to have this exact configuration. That is, they'll have a single covalent bond and 3 lone pairs. So we call these guys lone pairs, and we call that a bonding pair. Okay, so let's do another example. Let's do oxygen. So O2. Okay, here each oxygen molecule has how many valence electrons? We look on our periodic table. It is in period 6, so it has 6 valence electrons each. So we have a total of 12 in the oxygen molecule. So 12 valence electrons. We start by a Lewis structure. With a skeleton structure. Okay, so that counts for 2, and now we have 10 more electrons that we need to accommodate. Okay, the first thing we're going to do is try to accommodate these as lone pairs, but we have 10. That's going to be a total of 5 pairs, right? Which I think we're going to see pretty quickly will not work. So I'm going to try. I'm going to go 2, 4, 6, 8, 10. Okay, so that's 2, 4, 6, 8, 10, 12 electrons total. And that's all the electrons I'm allowed to use. And I've now satisfied the octet rule for this oxygen. I have 2, 4, 6, 8. I have not satisfied the octet rule for this one. So this is not a good structure. And so we need to figure out what can we do here to satisfy the octet rule for both of them. Both of the oxygens, right? And so what we're going to need to do is we're going to say, all right, this is not going to work with lone pairs, so we are going to increase the bond order. That is, I'm going to erase these 2 electrons. Whoops, not the atom. I'm going to erase those 2 electrons, and I'm going to put a double bond between them. Okay, so this is now, these oxygens are now sharing 4 electrons in what is called a double bond. Okay, and so now we have 2, 4, 6, 8 electrons associated with this oxygen, and 2, 4, 6, 8 with this. That tells us that that is a good solution. Okay, and in fact, the bonds between oxygen are entirely consistent with there being a double bond between the oxygen atoms and each oxygen having 2 lone pairs of electrons. Okay, and this simple model really helps us understand a lot about oxygen. Okay, so again, we've got lone pairs and we've got bonding pairs. Now, one thing I haven't pointed out up until now is that when we count our electrons to accommodate our octet rule, we're kind of double counting anytime we have shared electrons. So when we count, so when we count our octet here, we have 2, 4, 6, 8 for this oxygen, and we have 2, 4, and we count those again, 6, 8. And that's because they're sharing electrons, and so it's as if they both are satisfying that octet rule. Okay, so let's now do another simple molecule. Let's do nitrogen. Oops, I don't want green. I want blue. Oh, we'll do green. No, we won't. I want blue. Okay, so I want nitrogen. Each nitrogen has 5, so we have a total of 10 valence electrons. And we are going to start with our skeleton structure, N, and then that's 2 electrons, and we have 8 left, so that's going to be 4 lone pairs. Clearly that is not going to satisfy the octet rule, right, for both of our atoms. And so I'm going to start off by going, there's 2, there's 4, so that's a total of 6. I have 4 more, so I'm going to give it to that guy, I'm going to give it to that guy. Okay, so there's our 10 valence electrons, 2, 4, 6, 8, 10, but neither of these atoms has satisfied the octet rule. I could move one pair from one atom over to the other, but that's not going to do me any good because that won't satisfy the octet rule for both. Okay, so I'm going to start by erasing that pair, and I'm just like I did with oxygen, I'm going to draw a double bond. So now we've got a double bond, and we have 2, 4, 6, and 2, 4, 6, 8. So we've satisfied the octet rule for this one, but not for that one. So this is still not a good structure. So I'm going to do it again. I'm going to erase that one, that lone pair, and turn it into a bonding pair. And now 2, 4, 6, 8, and 2, 4, 6, 8. I have satisfied the octet rule for both of my nitrogens. I say, good job. That's a good representation for the nitrogen molecule as having a triple covalent bond. Okay, so this idea of bond order really is related to the nature of these bonds. And in our simple model, we define bond order as the number of covalent bonds that exist between 2 atoms. So a single bond shares 2 electrons, double bond shares 4, and a triple bond shares 6 valence electrons. And this term bond order, coined by Lewis, really denotes simply the number of pairs of shared electrons. Okay, and the relationship between the number of pairs of shared electrons and the nature of the bond is sort of summarized in this table. Okay, so if you have a single bond like you do in the fluorine molecule, and all of the halogens, by the way, we have a bond order of 1, and our bond length is about 1.4 angstroms. Okay, so a single bond has some bond length and some bond strength. Now, if you go to a double bond with a bond order of 2, your bond gets shorter and it also gets stronger. So it takes more energy to break this bond. Then you go to a triple bond, it gets shorter still and the bond gets even stronger. Okay, so single bonds are longer than double bonds, which are longer than triple bonds. Single bonds are weaker than double bonds, and they're also weaker than triple bonds. So it always occurs in that order. Okay, so the bond strength, triple is greater than double is greater than single, and the bond length, single is greater than double is greater than triple. So the bond order really gives you an idea of what that bond is like. Okay, so again, it's best to compare bonds of between similar atoms. So for example, carbon-oxygen bonds can be single, double, or triple. Okay, and here is the distance, the covalent bond distance, bond length. For the single bond, it's 143 picometers. It's 120 for that double bond and 113 for that triple bond. So a double bond isn't twice as short as a single bond. It's also not twice as strong as a single bond, but we just want to know the trend here. A single bond is weaker than a double bond, is weaker than a triple bond. Okay, so let's do one more quick example here and we will be done. Okay, let's do a little bit more complicated molecule. Let's do Ch2O. Okay, this is the formula of a compound called formaldehyde. Okay, so here we've got carbon has 4, plus 2 plus 6 for oxygen, right? So for a total of, I think that's 12. Okay, so we have 12 valence electrons. Okay, now again we're going to start with a skeleton structure, and we're going to need to know which one of these atoms is central. And the way that this is written kind of tells us, it basically tells us that the central atom is generally the least electronegative of the main group elements that are not hydrogen, right? Hydrogen can never be a central one. So that's going to be carbon. And we're not going to worry too much about having to figure that out because generally we're going to have some indication. In this, we know it because carbon is first. In cases where it's not so clear, there's going to be some indication to help us out. Okay? Certainly on a test, I'm going to basically tell you. Okay, so here we're going to write carbon is central, and then we're going to draw all of the other atoms attached to that carbon by single bonds. Okay? And when we do that, we have 3 single bonds, that's 6 valence electrons, so we have 6 left. All right, so we can do that in 3 lone pairs, right? So we go, okay, 1 lone pair, 2 lone pairs, 3 lone pairs. Okay, so we're done, right? That was easy. And we look, we've got 2, 4, 6, 8, 10, 12. We've used all our valence electrons. We have an octet for oxygen, 2, 4, 6, 8. Each of the hydrogens has single bond. 2, 4, 6. Carbon only has 6. That's not good because carbon wants 8. Oxygen is not the only one that gets an octet. So what do? Well, we got to increase our bond order. So I'm going to erase these 2. And I'm actually going to erase that as well to make it a neater double bond. I'm going to make that a double bond. Now my carbon is happy. It has 2, 4, 6, 8 valence electrons. Oxygen still has 2, 4, 6, 8, and we have still used all 12. And so I'm going to say good job. That's an excellent representation for the formaldehyde molecule, having double bonds between the carbon and oxygen, and single bonds to each of those hydrogen atoms. And it's important that we always use all of our valence electrons and we never add extras just to satisfy our octet rule. We can only use the correct number of valence electrons by adding up each of the valence from each atom. All right.